Welcome to our deep dive on reinforcement learning, from zero to hero. We'll be mastering sequential decision-making, starting with Markov decision processes and moving all the way to LLM-enhanced RL. What is reinforcement learning? It is the concept of learning through interaction. RL trains agents to make optimal decisions using a numerical reward, a critic, rather than labeled data, a teacher. The loop involves the agent observing a state, taking an action, and the environment returning a new state and a reward. The foundation of most RL problems is the Markov decision process, or MDP. It is defined by four core components: states, actions, transitions, and rewards. We also have the discount factor, gamma, which determines the importance of future versus immediate rewards. Crucial to the MDP is the Markov property, which states that the future depends only on the present. This means the current state must contain all relevant information needed to predict the next state. For example, in chess, the current board layout is sufficient for deciding the next move. The policy, pi, is the agent's strategy, a mapping from states to actions. The return, GT, is the total cumulative reward the agent expects to collect over time. Our objective in RL is to find the policy that maximizes this expected return. It is important to distinguish between reward and value. Reward is the immediate feedback after an action. The value function, V, is the total expected reward in the long run from a specific state. A state near a goal has high value, even if the immediate reward is 0. The Bellman equation is the mathematical core of RL. It provides a recursive secret. The value of your current state equals the immediate reward plus the discounted value of the next state. This allows agents to propagate reward knowledge backward from the goal to the start. A fundamental trade-off in decision-making is between exploration and exploitation. Exploitation means choosing the action you know is best. Exploration means trying something new to discover better strategies. The epsilon greedy strategy is a common way to balance this. One learning style is Monte Carlo, or MC, where the agent learns from finished episodes. MC methods require the agent to complete an entire game before updating its value estimates. While easy to implement, it is very slow and sample inefficient. Temporal difference, or TD learning, updates the agent's knowledge step by step using TD error. This method is much more sample efficient than Monte Carlo and forms the backbone of modern deep RL, allowing immediate adjustments of expectations. When RL meets neural networks, we get deep Q networks, or DQN. In complex tasks, there are too many states for a simple table. The solution is using a deep neural network as a function approximator to estimate values. DeepMind famously used DQN to achieve human-level performance in Atari games. Policy gradient methods offer direct optimization, adjusting the probability of taking specific actions instead of calculating state values. Proximal policy optimization, PPO, is the modern standard used in systems like ChatGPT. PPO ensures updates are not too drastic, preventing the agent from forgetting good strategies. We can categorize RL algorithms as model-free or model-based. Model-free is about doing. The agent learns by trial and error without understanding the environment's physics. Model-based is about thinking. The agent builds an internal world model to simulate and plan future moves. Monte Carlo tree search, MCTS, is a look-ahead planning algorithm, famously the engine behind AlphaGo. MCTS involves 4 steps: selection to balance exploration, expansion to add new moves, simulation to run a rollout, and backpropagation to update the tree with results. Offline reinforcement learning is the concept of learning exclusively from a pre-existing historical dataset, rather than requiring active interaction. This is crucial for high-risk environments like autonomous driving, where exploring through fatal mistakes is unacceptable. RL from human feedback, RLHF, is the secret sauce behind modern LLMs like GPT-4. It works in 3 stages. Humans label responses, a reward model learns human preference, and then PPO training fine-tunes the LLM to maximize that human-preferred reward. We are currently experiencing an unexpected RL renaissance. While scaling drove past AI success, simple prediction hit a ceiling. Labs discovered that verifiable rewards, especially in math and code, allow RL to train models to reason, leading to systems that solve PhD-level problems. LLMs are now being used as reward designers. Designing reward functions is often the hardest part of RL. For example, in the Eureka project, an LLM wrote a complex reward function that taught a robot hand to spin a pen as well as a human, a task too difficult for manual programming. In-context RL, or ICRL, allows agents to solve new tasks without updating their neural network weights. The agent's history of observations and rewards is fed into the LLM as context, and the model instantly implements an RL algorithm in its forward pass, offering fast adaptation. LLMs are also emerging as decision makers, providing high-level planning for robots. The LLM acts as the brain, while traditional RL handles the muscles. In the Seikan example, the LLM plans the steps to clean a spill, and RL executes the precise motor control to pick up the sponge. Multi-agent RL, or MARL, involves multiple agents interacting, which can be cooperative or competitive. The main challenge is non-stationarity. As one agent learns, the environment changes for the others, making it a moving target. Hierarchical RLHRL uses a divide-and-conquer approach by breaking long tasks into sub-goals. This solves the credit assignment problem by making feedback shorter and clearer. A high-level manager picks the goals, and a low-level worker executes the steps. Explainable RL, or XRL, aims to open the RL black box. XRL uses LLMs to translate the agent's complex policy into human language. The LLM analyzes the agent's history and explains the actions taken, such as why the agent chose to recharge its battery. Two major challenges remain in RL: sample inefficiency and safety risks. RL often needs millions of trials to learn simple tasks. Furthermore, random exploration is dangerous in the physical world. An autonomous car cannot safely explore by driving off a bridge. The next frontier is AGI and robotics through multimodal RL, where agents can see, hear, and act simultaneously. Experts project the market impact of RL to grow exponentially, supporting massive growth by 2037. To summarize, some practical takeaways. Start with MDPs and define states clearly. Use TD for speed with one-step updates. Leverage LLMs to design your reward functions automatically. Finally, think offline and use historical data before real-world deployment. You now have the roadmap from basic agents to LLM-powered reasoning engines. Thank you for joining this deep dive on reinforcement learning. Be sure to join the AI community on Dev Basics with AI. Keep building, keep exploring.